Hey everybody, welcome back to my channel. A while back, I covered a few fundamental topics about PyTorch. Today, we're gonna take it a step further. We're gonna learn about transfer learning. Now I know that PyTorch has already released documentation and tutorials of transfer learning, but on my end, this documentation seemed a bit too complex for me. So this video is for people who also found this tutorial a bit too complex. Today, I'm going to be teaching transfer learning in a very simplified format. So some of you might have questions about transfer learning. What is transfer learning, you might ask? Well, let's take a problem. Let's say I build a model, a completely custom model, and I have training data, for example, image data. Sometimes we have a problem where our model is not complex enough or not deep enough to understand the patterns in training data. So yeah, the patterns can be too complex, or if our model can still pick up the pattern, sometimes it does not perform well enough, or any other model. So this is where transfer learning comes into play. Here we take an existing model that already works for image or text data, and then we can adapt it to our needs. So for example, we can change the parameters, or we can train these models with more data. Let's now talk about the model that we're going to be using. In this video, we're going to be using the ResNet-18 model. This is a very capable PyTorch model, great for image recognition. So now that you know what transfer learning is and what it's used for, let's go to Google Colab to write some code. Okay guys, here I am in Google Colab. The first step here would be to download a dataset. So here I have a dataset. It's a human action detection dataset. So basically these are just a bunch of images and they have labels on them. So basically an image has a label of calling, clapping, cycling, and so on and so forth. We're gonna look at it further when we write some code. So first I'm gonna have to download it. So if I click on the download button, here we have a code snippet. I'll copy it, I'll go back to Google Colab, and then we paste it like so. And then I run it. So while it runs, it's important to know that I'm going to be using the GPU for today. That's because to train ResNet, it takes a lot of time. Okay, so here we have the path to our files. So it's in the cache. I want to copy the dataset files from the cache to the content directory. So I create a new code snippet. And here I go cp-r. So I copy, and then my dataset path, which is this one. I copy this, I paste it here, and then /content/data, and then I run it. And now it's been copied. So within data directory, we have datasets. Within human data, we have test and train data. And within train data, for example, within the calling label or the calling folder, we have our images. So let me expand it. Let's click on this one. Okay, so here we have an image with the calling label. So let me just collapse it and let's move on. I'll now create another code snippet. And now our next step here would be to create a transform. Basically, transform allows you to transform your data sets into machine readable data. Furthermore, you can also do a lot of stuff within transform. Not just converting an image to a tensor, but you can also crop, or you can also flip or manipulate images to your liking. So anyways, let's create a transform. So here I can go import from torch vision.transforms. So I'm going to be using the v2 API, import v2. There's also a v1, but I'm going to be using v2. And then we're going to create a transform. So transform_train. So a transform for our training data set. Here I go v2.compose. And then what I can do here is I can go v2.resize 224 by 224. This is recommended by a few tutorials online, 224 by 224. And then I can do a random horizontal flip. So random horizontal flip. And I'm going to explain it to you later on. So p equals to 0.5, v2.image, to image, comma, v2.to the type. So I convert this image into torch.float32. And then I can scale it as well, comma, and then I normalize it. So v2.normalize, and basically these values, so mean is an array of 0.45, 0.45, 456 and 0.406. Then there's another parameter called standard, so it's STD or standard deviation, whatever you call it, 0.229, 0.224, 0.225. Anyways, let me explain you whatever is happening here. So first of all, when we feed the image into a transform function, what we want to do here is we want to resize it. And then we augment this data. We augment this data set using a random horizontal flip. So basically, this allows the model to generalize the data set better and learn the patterns better as well. Later on, we have these two lines, to image and to 2D type. So basically, these convert the images into proper tensors. Afterwards, we have this dot normalize function, and I'm not really sure what they mean, but they have been recommended by the documentation. So around here we can see we have to normalize these images using these values and these STD values as well. Anyways, now that we have the transform for our training dataset, we have to create a transform for our test dataset as well. So transform underscore test v2.compose, and then some of the code is going to be similar here as well. So it's v2.resize, I copy and I convert it into a tensor, copy these as well. And then at the end, I normalize them. So I copy this and paste it here. So some of you might be asking, why are we using separate transforms for our test and train data sets? Well, the keyword here is data augmentation. So for example, let's say you're training your model on images of cats. Here, when it comes to this image, the model is going to think to itself that cats only have their noses pointed towards the right. However, in the real world, that's not really the case. In the real world, cats can also have their noses pointed towards the left. So data augmentation, so for example, random flips, crops, or other effects can help the model generalize better and learn better on our dataset. By using transforms, you're creating infinite variations of your data. However, when it comes to test transforms, we want consistency. That's why we're not really doing any augmentation within the testing stage. Anyways, let's head back. So the Fraunhofer Institute, they have a useful article on data augmentation for AI, and I really recommend you guys on reading this so you can get a better idea on data augmentation. Anyways, let's head back to writing code. Okay, so I have this code here. Let's run it. So we have a problem here. The T is not supposed to be capital here and here. Let's run it again. What's wrong here? Torch is not defined, so I import torch like so. So import torch. Okay, no errors so far. So now let's create a code snippet and apply our transforms to our data set. So here I create a few variables I call train directory, and let's see the train directory, which is datasets, human data, train data. So I copy the path, and then I do the same for test directory. So we have copilot or autocomplete here, and then let's apply our transform. So train data equals datasets. Looks like I forgot to import datasets. So from torch vision, I import datasets, and then datasets.image folder root is train directory. So the directory to my train dataset, and then I apply my transform like so, and then I do the same to my test dataset. And then we also have another parameter called target transform, and I set it to none, and I do the same here as well. Target transform is none. And then at the end, I want to see how my train data and my test data variables look like. So let's run it, and here we have the result. So here we can see the train data has around 15,000 images, and the following transforms are already applied. And then we have our test data set. So it has around 3,000 data points or 3,000 images with these transforms. Okay, so one thing is that we have around 15,000 images to train our model. The problem here is that since we have so many images, we're gonna run out of GPU memory. Furthermore, it's gonna be a huge strain on our CPU as well. So here we're gonna create a data loader. So here I go train loader equals data loader. Let me just scroll down, and it's trained data. So we pass in our data set, and then we have a batch size of 32, and then I shuffle it as well for data augmentation. And let me just fix my imports. So here I go from torch.utils.data import DataLoader. So batch size, by the way, is just how many images you want per batch within your loader. And then we're gonna have a test loader. So test loader equals data loader. So test data, then we have a batch size of 32, but we don't shuffle it. And then let's run it and see if we have any problems. Okay, so no errors so far. And then now I want to set up my model. As discussed earlier, we're going to be using the ResNet-18 model. So here I go model equals models.resnet18. I need to fix my imports. So from torch vision import models, and then here I have to pass in my weights. So the default weights is image net 1k underscore v1. Furthermore, in this video, I want to set up device agnostic code as well. So device equals torch.device CUDA if torch.CUDA is available. Otherwise, I use a CPU, and then let's run it. Okay, so now that my model has been downloaded, I want to see the parameters of this model. So here I'm going to use something called torch info. So first I would have to install it. So I go pip install torch info. Let's install it. Now that it has been installed, new code snippet, and then from torch info import summary, and then I get the summary of my model. So my model, and then I pass in the input size. So 32 must be the number of batches, 3 is the color channel, so red, green, blue, and 224 here is the height and width. So let's run it and see what we get. Okay, so now that my code has run, here we can see the number of parameters and the number of layers that we have in our model. So let's scroll down, and the most important layer here is the linear layer. Within this layer, we get our outputs. So here notice that our output shape is 32, 100. Sorry, not 100, 1000. This means that ResNet-18 is capable of detecting around 1000 classes of images or 1000 different labels of images. However, the problem is we don't have 1000 labels. I think we have fewer labels. Let's check. To get the number of labels, I can go train data.classes. So the number of classes or the number of labels. Let's run it. So here we have our labels or our classes. I'm just going to call it classes from now on. And then we can get the length. So we have around 15 different classes. So one thing here is I forgot to visualize some of these images. So I create a new code snippet, and let's take an image. So first I would have to import some stuff. So from pil import image, from numpy as np, and then import matplotlib as plt. First, let's get an image. So img, not npg, img equals image.open, and then the path to my image. So within my train data, let's get a calling image. I'll just take this one. So I copy path. Let me just collapse it because my computer gets really slow. And then I plot it like so. So I go image plot equals plt.imshow image, and then plt.show. Let me close it and let's run this code. Looks like I made a syntax problem. Sorry, import. Let's run it again. Okay, so here as you can see, we have the following output. We can also pass this image through our transform. Let me just copy this. I copy this, paste it here, and then image equals transform underscore train. So I pass it through my train transform image, and then plt.imshow image. Let's see what we get. Okay, so here we have a problem. It's a shape error. This is because our transformed tensor has this shape where 3 is the RGB values and 224 by 224 is the height and width. However, matplotlib expects height and width to come first and the color channel to come last. So I would have to permute this. So let's permute it like so. So I go image.permute, and the index of 1 comes first. So 1, the index of 2 comes second, and the index of 0 comes last. So now let's run it again. Okay, so here as you can see, this is the image through my transform. And recall earlier, our transform has a horizontal flip. So let's see how the horizontal flip looks like. If I run it again, hopefully it should flip. Great. As you can see, the image is now flipped. This means that our transforms work just fine. Anyways, getting back into topic, recall that my linear layer has this output shape and we will have to change this linear layer. So I'm going to scroll down and let's change this layer. So here I go num_features and I want to keep the in features parameter, which is 32. To do so, I go model.fc, which is final classifier in features. Let's just see what num features looks like. And it's 512, not 32. My mistake, sorry. Let's see how out features looks like. Maybe I'm wrong here as well. It's around 1000. Okay, so I was correct. Anyways, model.fc, so the final classifier is nn.linear. So I want to preserve the linear layer. And the in features is going to be num features, so 512. And the out features is going to be the length of the trained data classes or the labels. And then finally, I'm gonna transfer this model to my GPU. So I go model equals model.to device and let's run it. Okay, so I have an import error. Looks like it's very common here on the channel. Anyways, to fix it, I go from torch import nn. Okay, let's now move on. Let's now perform some inference on my image, which was this image. So here I go image equals image.to device because I want my image and the model to be on the same device or the GPU. And then to perform inference, I go model.eval, then with torch.inference mode, ypreds equals model image. So I have to unsqueeze this image, by the way. Dim equals 0. And then here we get the logits. So to convert these logits into proper probabilities, I'm going to have to use the softmax function. So ypreds equals torch.softmax ypreds, and it's going to be done across the dimension of 1. And then when we get the probabilities, I want to get the index of the maximum probability. So torch.argmax ypreds dim equals 1. And then at the end, I want to print out what ypreds looks like. So let's run it and see what we get. Okay, so here we have a problem. That's because I did a permute earlier. So I'm just going to copy this. I'll just copy both of these lines and then let me just remove this, place it here, and then image equals image.to device. So basically the unpermuted image. Okay, so here we have our answer. And obviously I expect it to be wrong because our model has not been trained yet. So now our next step here would be to set up our training loop. So let's set up the training loop. I create another code snippet and let's start by creating a loss function and n.cross entropy loss. And then we do an optimizer equals torch.optim. So I'm going to be using the atom optimizer, and then params equals model.parameters, comma, and then the learning rate. So the first starting point here is going to be 1e minus 4. And then let's run it. Okay, so no errors so far. And then for my training loop, I want to create an accuracy function. And this function will tell me how many items or how many predictions my model got right. So def accuracy underscore fn. The first parameter here is going to be y true, comma. The second parameter is ypred. And I've done this in a previous video, so I'm not going to be covering this function in detail. Correct equals torch dot equals, so I get the number of correct items between these two tensors, ypred dot sum dot item, and then I get the accurate predictions in terms of percentages. So correct, comma, not comma, divide by length of y predictions multiplied by 100. And then at the end, I return my accuracy. Let's run it. Okay, no error so far. And this time I want to create my function on training this model. So here I go def train model, and here I'm going to go model, the parameters model, and then train loader. I don't want a test loader. I want the loss function, comma, and then the optimizer. So within this function, I go model.train, and then let's create a few variables. So running loss equals 0, number of correct items 0. Actually, it's better to declare it as accuracy. And then here I go for batch, comma, x, comma, y. in enumerate. So I want to loop through my data set or my data loader. So where batch is the batch number, X is the input, Y is the output. So here I can go X comma Y. So I want to transfer them to the GPU. So X.to device comma Y.to device. And then here I go ypred. So I get the model predictions in terms of logits. And then I get the loss. Loss equals loss underscore function ypred comma Y. So here it's going to calculate the difference between the prediction and the correct label. And then I can add the running loss with the current loss. So it's loss.item. And then all the normal parts of our training loop. So optimizer.zeroGrad, loss.backward, and then optimizer.step. Furthermore, I also want to get the accuracy. And then at the end, I want to get the average of the loss and the accuracy per batch. So I'm going to get the average. To do so, I go acc divided by length of the train loader, and then same for the running loss, and then at the end I return the running loss and the accuracy. That's it. So now let's run this code. No errors so far. That's great to see. And now I want to create another function for my testing loop. So test model and then model comma loss fn comma test loader. So I first go model.eval and then I do the same thing. So test loss is 0, test accuracy is 0. So basically very familiar to what we did earlier. And then with torch.inference mode, I loop through my data set. So I send it to the device. I get the predictions and then calculate the loss. And then I append this loss and the accuracy. So it's ypred is ypred.argmax, and then ytrue is the correct label that's coming from a data set. And then as always, I would have to get the average. Looks like Gemini is helping me too much today. So now I return test accuracy and test loss. Actually, let's make it a bit consistent. So loss came first earlier. So test loss here and test accuracy here. And let's run it. Okay, no errors so far. Let's now actually run these functions. So I create a variable called epochs, and let's use 10 epochs today. And I also want to calculate the time. So import time. And then for epoch in range epochs, let's actually start the timer. So start equals time.time. And then train loss, comma, train accuracy equals, so I train the model. Let's use keyword arguments today. I just want to be sure. Model equals model, comma. What's next? Loss function is loss function. Optimizer is optimizer. And then we have our train loader, which is train loader. Then I'm going to do the same for my testing step. So test model. Model is model. Loss function is loss function. And we have test loader. So test loader is test loader. And then at the end, I calculate the time taken. So I create a end variable, print time taken, and then end minus start. Okay, so let's run this. Actually, I have to run this first. And let's run it. So it's going to take some time for it to train. So I'll meet you guys after it's done training. So while running the code, I forgot to print out the losses and the accuracies. So I'm going to do it now. So epoch, and then train loss like so. And then I get the train accuracy, train acc, and then test loss, test accuracy as well. So test accuracy. Anyways, very sorry for the small detour. Let's run it and hopefully everything works out just fine. Okay guys, so now that my model has been trained, we have an accuracy of around 98%. However, there's one thing we can improve. We can use something called a scheduler. Some of you might be confused on what a scheduler is, so I'm going to explain it to you now. So for example, assume for a minute that you have a TV and your TV remote is behind the couch or under the pillows of your couch. Now let's say you're trying to blindly reach for that TV remote. So in the beginning, you're going to move your hand 5 or 6 inches to the left, to the right, or in any other direction to find the TV remote. So a while later, you realize that your TV remote is near your hand. So you reduce your hand movement by a few inches, or in other words, you reduce the learning rate by a few percent so that you could accurately reach for the remote. Similarly, in PyTorch terms, let's say the model is near to the desired output or the desired value. However, let's say the learning rate is too high, so it cannot adjust its parameters properly. So the scheduler will reduce the learning rate so that it can accurately reach the desired value. There's already an excellent video on schedulers that will help you understand how schedulers work. Anyways, that's how schedulers work in a nutshell. In this video, I'm going to be using the reduce LR on plateau scheduler. There are a few schedulers that you can use, but I'm going to use this one. Anyways, so to use the scheduler, I'm going to scroll up around here and we can define the scheduler. So here I go scheduler equals optim dot, actually let's do torch.optim dot LR scheduler dot reduce LR on plateau. And the first parameter here is going to be my optimizer, comma, mode. We have a mode and the parameters here. So for example, if it's going to be min, the learning rate is going to reduce if the quantity that we're going to monitor is decreasing. So let's do min. I believe that's the default parameter as well. And then we have something called a factor. So the factor by which the learning rate will be reduced. I'm going to set it to 0.1, comma, and then patience. So the number of epochs to wait before the scheduler kicks in. It's covered around here. Anyways, let's rerun this code once again. So I'm going to scroll down and we're going to be using the scheduler within the test step. So here I go, scheduler. And I'm using scheduler within the testing step because according to the code snippet here, the developers of PyTorch are using the scheduler to monitor the validation loss, not the training loss. We don't have validation here, so I'm going to be using the testing loss instead. And then within my function here, I'm just going to go scheduler.step test underscore loss. Now with that being done, I would have to rerun some parts of my code here. So I would have to redefine my model because I want to start from scratch this time. And this code snippet will run again. Let's scroll down more. This code snippet will run again as well. And this code snippet will run again as well. Okay. Same for this one. And just to be safe, I'll rerun this one as well. Now, with that being done, I will have to pass in my scheduler within my test model execution function or my test model function. So this time it's scheduler equals scheduler. That's it. Let's run this code and hopefully we should see the same or even better accuracy. Okay guys, now that my training code has been complete, as you can see, my training accuracy has been increased. Before it was 98% and this time it's 99%, nearly 100%. Not a big difference, but it's still a difference. Let's now try performing some inference on our trained model. So let's choose an image I took earlier, this one. I'll just copy this code. I paste it here. And this time I don't want to plot it. We already know how the image looks like. So to do inference, I go model.eval and then image. I transform this image using my test transform. So here I go image and then I transfer it to the GPU like always, device. And then with torch.inference mode, ypreds equals model image.unsqueeze. So I have to unsqueeze it. Dem equals 0. By the way, if you're not sure why I'm performing an unsqueeze, you can just run this code without the unsqueeze part and you'll know you'll get an error. Anyways, and then I do a softmax. So torch.softmax, ypreds dim1, and then I get the argmax. At the end, let's see what ypreds looks like. So it's an item of the number 0. And then I believe we have class names as well. I think we don't have class names. I would have to define class names. So train data.classes. And then let's see what class names looks like. And then I pass in ypreds.item. So here basically ypreds.item is 0, so it has a label of 0, and I'm getting the name of that label or a human readable version of that label. So if I run it and it's calling, and according to my trained dataset, calling is correct. Let's try using another image. So within datasets, let's use a test dataset or an image from my test dataset. Let's choose from drinking. I'll copy this one. Let's close it, paste it like so, and let's run it again. So the model says it's drinking. That's great. So that means my model is performing just fine. As the next step here, I can even build a confusion matrix. So if you don't know, a confusion matrix is kind of like a table where you can check how accurate your model is when compared to its predicted labels and the actual truth label or the true data. So I'm going to make a function. Let's call it make confusion matrix. And then model test loader. And then I want to perform evaluation. So here I can go by true. So the correct labels from the dataset, and then ypred. So the predicted labels from my model. And then with torch.inference mode for inputs, comma, labels in test loader. So I loop through my test dataset, inputs, labels. So like always, I want to set up device agnostic code. So I transfer this data to the GPU or the CPU, doesn't matter. And then I get the outputs. I go outputs equal model outputs, not outputs, inputs. And then I go test preds torch dot softmax. So basically what I was just doing here. And we can even compress this into one line dot argmax like so. And I believe we have another parameter. So I have to squeeze this. Dim equals 0, and then for my argmax it's gonna be dim equals 1, and then yTrue.extend labels. So sometimes we have problems during plotting. That's because matplotlib or other plotting libraries want data to be on the CPU. However, our data is on the GPU, so then I would have to transfer it to the CPU and then convert it into numpy. ypred.append. I believe we can add append here as well. Test pred.cpu and then to numpy. And then anyways, ypred equals np.concatenate ypred. So I convert this array, or I flatten this array via numpy. And then I convert this numpy array into torch tensors, torch.tensor ypred. I believe we have errors later on if we don't do this step. Anyways, here I can go test loader.targets. So basically these are the labels. Let's see dot targets. Whoops, looks like there's a problem. It's not test loader. I think it's test data. Yeah, it's test data. So I remove this and it's test data.targets equals torch.tensor test data.targets. So here I'm converting my array of labels into torch tensors. And then finally, let's create a confusion matrix. So confusion matrix. Looks like I have to import it. So import, it's actually from torch matrix, import confusion matrix. And I believe we have an installed torch matrix, but I will install it later on. And then from ml extend dot plotting, import plot confusion matrix, then import numpy as np. I believe we have already imported numpy, but I'll just add this code just to be safe. Anyways, so confusion matrix accepts a parameter called numClasses equals len class names task multi-class, and then conf mat tensor. Now I know this code is a bit long, but bear with me here. Anyways, pred equals ypred, and then target. So the target labels or the true labels are test data.targets. Anyways, fig comma ax, I go plot confusion matrix conf mat equals conf mat underscore tensor, and then I convert it into numpy array comma class names, and then I figure size. So let me double check my code here. Let's see if I've written everything correctly. Anyways, it seems fine to me. Now I'll walk you through what I did here. So first of all, I set up my model in evaluation mode, and then I want to perform inference on it. While performing inference, I looped through the whole test data set, and then I got the correct values and the predicted values. Later on, I converted my data so that it could be used within my conversion matrix. Anyways, let's run this code. Actually, I think we're gonna have errors. Let me just install these modules. So here I go capture, and then pip install torch metrics and mlx extend, and let's run it. Okay, so now it's installed. Let's run this code snippet. Okay, so we have an error here. Okay, so I found out the error. So I have to remove mlextend. Basically, it's the wrong package name, and mlextend is already included, so I don't need to install it. But anyways, let's run this code again to install my pip package, and while it runs, okay, so now it's run. Let's run this as well. Hopefully we don't get any errors. Okay, so now it ran. So now let's use this function. So here I go make confusion matrix model comma test loader. So let's see what we get. Okay, so we have an error. I know the error, it's actually labels, not label. Let's rerun this again and rerun this again. So I still have the error, it's inputs. I'm getting so tired of this. Run and run. Okay guys, so here we have our confusion matrix, and this confusion matrix doesn't really make any sense. So for example, here according to this table, the model is predicting the calling label correctly only 25 times. It doesn't really make any sense. This is because my model has around 99% accuracy, so it should be correct. So to fix this, I added this line where I'm using the torch.max function, and instead of test spreads here, I'm gonna pass in predicted. And then when we rerun our code, we finally get a confusion matrix that actually makes sense. Another way to fix this code is we can remove this predicted variable, and I made an error here, so it's dim equals to 1. So let's run it and hopefully we get the same result. Looks like predicted is not defined, so it's test spreads. So I run it here and I run it again. Alright, so a few seconds later, my code has now run and we have the same confusion matrix as before. So for the next step here, we can even try to find ways where we can make our training loop or a training process more efficient. So for example, let's scroll up and let's go to the summary part of Torch info around here. And as you can see, our model is really large. And while training, I believe it's not really necessary to retrain or fine-tune all of these parameters. Essentially, as you saw, we were only concerned with the linear classifier layer. This is also covered within the PyTorch documentation around this chapter where it freezes the parameters. This means that during training, we don't want the model to readjust all of its parameters or all of its layers. We only want to fine-tune or retrain the linear layer. In theory, it takes up less GPU, memory, and time. So let's do this now. So I'll scroll down, create a new text, and let's add a heading, more efficient, actually not more efficient, freezing parameters. And let's write some code here. So I'll scroll up where we redefine our model, or we initialize our model around here. I'll scroll down all the way here, paste it here, and this time I'm gonna go model underscore 2 because this is our second model. I remove this, and then here I go for param in model 2 parameters dot parameters. I want to freeze all of the parameters, so param dot requires grad equals false. However, I want to edit the final linear layer, so now features equals model underscore 2 dot fc in features, and then we basically edit the linear layer like before. And then I transfer this model to my GPU, so .2 device, and then my optimizer optim.atom model underscore 2 dot. So here it's a bit important to know that this time we're not going to do dot parameters, we're going to do dot fc dot parameters. So this means that this time I don't want to train all these parameters, but just the last final classifier layer. Anyways, and then I set the learning rate 1e minus 4, and then I set the loss function and n dot cross entropy loss, and then I set my scheduler as well, just like before. So optim dot lr scheduler, sorry, it's torch dot optim dot reduce LR on plateau, whatever you call it. And let's add torch dot here as well. And let's run it. Okay, no error so far. And then this time I'm gonna run my training loop once again. So import time, start equals time.time, define my epochs, 10, and for epoch in range, range 10, train loss, model 2, loss function, and then I pass in my train dataset. Same for my test loop, model 2, loss function is loss function, test loader, and then scheduler. And then at the end, I will print out these values. So epoch, train loss, train accuracy, train test loss is test loss, and then test accuracy is test accuracy. When that's done, I calculate the time elapsed. So print time taken. Looks like I've made an error. It's not curly braces here. Time taken and minus start. So now let's run it. Alright guys, now that my training is complete, here as you can see, the time taken is around 693 seconds. And if we scroll up, here as you can see, when we trained the model from scratch, it took 929 seconds. So this means that freezing our parameters and then training our model takes lesser time. However, the trade-off is that we have a lower train accuracy. Now obviously I can rerun this training code, but it's important to know that freezing your model comes with trade-offs. This is because since we're not training the model from scratch, there is a chance that the model's pre-trained parameters are not really well suited to the current dataset. Anyways, I'll make it fast since I'm almost out of resources. So I'll just plot the conversion matrix or the confusion matrix. So here I go make confusion matrix, and then my model this time is going to be model 2, and then test loader. That's it. Actually, I think I have to do keyword argument. So test loader, and let's see how it looks like here. Okay, so here as you can see, we now have a confusion matrix. Here as you can see from the train accuracy, it was kind of obvious that model 2 is not as accurate as model 1. So for example, the model predicted the calling label correctly 82 times. However, if we scroll up, the first model predicted the calling label correctly 148 times. So yeah, freezing your model comes with trade-offs. So that's it for today. In this video, you guys learned about transfer learning and how to fine-tune the ResNet-18 model. Furthermore, you also learned about freezing the model along with image transforms. If you guys have any questions, any opinions, or any suggestions, let me know within the comment section below. Till then, bye bye and see you later.